Hello Mindsetters, welcome to today's grade 11 physical sciences show. Today we have a special revision lesson on chemical change. We have selected highlights from lessons shown earlier in the term to help you revise this term's work. So please post your comments and your questions on our Facebook page or on Twitter @LearnExtra so we can help you with your revision. You can also download the show notes for today's lesson from learn.mindset.co.za or click on the link on our Facebook page. Now it's time to get on with today's lesson.
Here is a question here. All right, it says use the table table of bond energies to calculate delta H. So we're going to calculate for delta H for the following reaction, okay? We've got a reaction between hydrochloric acid and bromine, so that should be Br2 as you always know it. It should be like that, right? And Cl2 the same way. Now, when that reaction takes place, we're forming HBr and Cl2. Is this reaction exothermic or endothermic? So first thing, let's find out the energies. What I did, okay, was to go back to the table and find out the bond energies from the table so that we don't have to flip all the time and waste time. But then let's go back to the table because you are to use it. So for this question, you would be provided with this table here. For example, look at it. I've got HCl, so I would take that energy there to break that bond because that bond is going to be broken. It's part of the reactants. Part of the reactant, I've got HBr, this one here. So that's the amount of energy is going to be broken. We need that energy to break that bond there. So I've taken that, I placed it on that page there. We also know that chlorine is going to be formed, so that amount of energy is going to be released per mole of Cl2 formed, and bromine, okay, that amount of energy will be released per bond of Br2 formed. Okay, now let's just move on to the question itself now. So these are the energies that you see there, okay? Now let's move on. It is per mole, so if you look at this reaction, I've got 2 moles of HCl reacting with 1 mole of that. So energy of reactants would be equal to 2 of what? The HCl, the energy is that one. You need 431 kilojoules to break 1 mole. So if I've got 2, I'll need twice as much. Plus, for Br2, I need that amount of energy to break that bond. So it will be plus 192. Okay? So that will be the energy of the reactants. And for me to get that, I can just quickly make use of the calculator here. Let's use it. I've got 2 times 431, okay, plus 192. Okay, so I need 1054 kilojoules of energy. Okay, so it's 10 or 1054 kilojoules of energy. Okay, needed here. Now, for the products, I've got this. So I'll say enthalpy that would be released by the products. If you look at the product, I've got 2 HBr, so it will be twice the energy needed or the energy released when the bond between hydrogen and bromine is formed. So it will be 368. Plus Cl2, 1 mole of that. And then with Cl2 from our table, what do we have? Cl2 is 243, so we'll say plus 243. And what will that be? Quickly, let's make use of a calculator. Okay, so I've got 2 times 368 plus 243. And what do I get? I get 979. 979 kilojoules. Then this is actually kilojoules per mole okay, for every mole formed or broken. Now, change in enthalpy, okay, should be equal to. Now, I want to take you back to the formula so that we see where all this come from. Look at this. Energy change, which is this one here. Energy change here. It's given by energy absorbed minus energy released, okay? So my energy absorbed is the energy that was used to break the bonds, okay? So energy, total energy absorbed minus total energy released, okay? So that will be equal to, absorbed is 1054 minus released, it's 979, and then this works out to be, use your calculator quickly, so you've got 1054 minus 979, what's your answer? It's 75, so you've got positive 75 kilojoules per mole. That is the difference between the energy absorbed and the energy released. Okay, now if you go back to the question here, it also said to us, or wanted to know from us, is this reaction exothermic or endothermic? Now from the change in energy, you can tell that the reaction is endothermic. Why endothermic? Because the change in energy is positive. Okay, so we've got a positive overall change in energy. Right. Now, coming to question number 2. Let's have a look at question number 2. Question number 2 says, in the following energy profile diagram, the x-axis represents the extent of the reaction, whilst the y-axis represents the energy of the reactants or products. Okay, so there is the graph there. 2.1, provide names for labels 1 to 4. Now let's have a look at it. Look at number 1. What is number 1? 1 is your activation energy. That is the energy, the minimum energy required, okay, to get that reaction to start going. Activation energy. Number 2, you look at number 2, that is number 2. That is your delta H, okay? So delta H, or you can also say this is the heat of reaction, okay? Right, and then 3, where is 3? You look at 3 there. Wow, this equation here, or this chemical reaction here, we need to be careful about. Look at that. There is a double arrow there that tells us that the reaction is reversible. The reaction is reversible. And because it is reversible, it means it can go backwards. These 3 here, 3, you can tell if these now become the products and, the reactants, and A and B are your products. It will mean that 3, it's your activation energy. Again, now activation energy, you can be specific and say activation energy for the reverse reaction. Okay? Activation energy for the reverse reaction. And that would mean that even for the first one there, we can actually go there and be specific as well and say this is activation energy for the forward reaction. Forward reaction. Okay? So in that way, we would have answered our question fully. All right. So that was number 3. Number 4, what is number 4? Number 4, it's that point there. that is where you have your activated complex. So number 4 represents your activated complex. Right. Calculate the activation energy for the forward reaction shown on the graph. Now look at it. Activation energy, reactants start from there, activated complex at 600. So the activation energy is equal to energy of the activated complex minus energy of the reactants. Energy of the reactants. So that will be 600 if you look at the diagram minus 100, and that equals 500, and this is given in kilojoules per mole if you look at the vertical axis here. Okay, kilojoules per mole. Right. Now moving on, 2.3, calculate the overall enthalpy of this reaction. Okay, now delta H would be equal to energy of products minus energy of reactants, and that will be equal to, if you look at the energy of products, they are at minus 150, energy of reactants at positive 100. So products minus 150 minus plus 100. This will work out to give you minus 250 kilojoules per mole. That tells you that this reaction is, of course, exothermic. All right? It tells you that. I wasn't asked to do that, but that tells me that's what's happening. Now, draw a sketch to show the effect of a catalyst, okay? We know with the effect of a catalyst, if I'm going to use an exothermic type of a reaction, okay, and exothermic type of reaction, okay? So reactants there, products there. If I supply a catalyst, the catalyst will lower the energy hill. But I need to be conscious, because it is only lowering that energy hill. It is not going beyond this, because it can't lower and it can't have an effect on the delta H. It can't have an effect there. It can only have an effect on the activation energy there. Okay, so if you look at this, you can say that was the starting point. So look at how much energy is needed now as opposed to the total amount of energy needed earlier on. So that is your activation energy. It lowers, all right, lowers the energy, the activation energy. Let me draw it like that so that this is let me show it nicely here. All right, so I have it like that. Okay, so that is how the energy will be affected. Okay, so you can say that is chemical potential energy and how the energy hill is affected in that way, right? So moving on, let's have a look at this question here, question number 3. During the process of cellular respiration, glucose is broken down to form carbon dioxide and water according to the following equation, okay? So glucose now is broken down. This is actually a combustion reaction. The reaction is catalyzed by enzymes. So what do enzymes do? They act as catalysts. The change in potential energy during this reaction in the human body is illustrated in the graph below. Okay, there we go. We have the graph there. Use the graph to answer the following questions. Is the breakdown of glucose an endothermic or an exothermic reaction? All right, give a reason for your answer. This is an exothermic reaction. Why? Exothermic. Why? If you look at this, that is energy of products, and that is energy of reactants. So delta H here, it's less than 0, and that is the reason. Delta H is negative, or you can just say delta H is less than 0. Okay. And 3.2, explain. Okay, explain how the enzymes influence the rate of the reaction. Okay, enzymes in this case are acting as catalysts. Okay, that is what they are doing. So if they're acting as catalysts, what are they doing? They speed up the rate of reaction. Speed up the rate of reaction. If you want to be specific, you would say they speed up the rate at which glucose breaks down to form, okay, carbon dioxide and water, or burn in oxygen to form carbon dioxide and water. Okay, you can actually say that. That is what it is happening, and that is what the role of the enzymes is there. So basically, this is about energy changes in the chemical reaction, the type of energies involved, delta H, chemical potential energy, enthalpies, and of course, the issue of catalyst, where a catalyst is used to speed up that rate of reaction.
Okay guys, I hope you are enjoying this revision session. If you are struggling and need help, please post on the page or send your questions to the Learn Extra Help Desk. The links are on our Facebook page. But now it's time to take a very quick break. Don't go away, we'll be right back. Welcome back from the break, guys. Doing revision is really important, so I hope you are enjoying this lesson. I'd love to chat to you on our Facebook page or on Twitter, so please let us know how you are doing. Enough of the chat, now it's time to get back to some more revision.
Question number 1. Write down balanced chemical equations for the following reactions. 1.1. Okay, what are we looking at? We're looking at sulfuric acid reacting with calcium carbonate. Now, people, the key here is also that you need to be able to write down the correct chemical formulae of these substances so that you can be able to see how they react and be able to balance your chemical equation as well. So here you have got an acid reacting with a carbonate. If I've got an acid reacting with a carbonate, if I have an acid reacting with a carbonate, I know that the product is going to be salt plus water plus carbon dioxide. Okay, so I can write, yes, all right, so I'll have H2SO4, that is sulfuric acid, plus calcium carbonate, it's CaCO3. This will give me, the salt is going to be calcium sulfate. So it's calcium sulfate, okay? And it's like that. I don't have a subscript for calcium because it's 2 plus and 2 minus. 2 plus from calcium, 2 minus from the sulfate ion, plus water. Okay, plus water plus carbon dioxide. Okay, can we balance this? Do we need to balance it? Let's have a look. H2, how many H's do we have there? 2 on the right. Sulfur 1 on the right. Oxygen 4, 7. And then 4, 5, 7. So that is balanced. Calcium 1, calcium 1. Carbon 1, carbon 1. So this equation here is balanced as it is. Okay? So I don't have to put anything to balance it. It is balanced as is. So that will be it. All right. Next, nitric acid and magnesium hydroxide. This is an acid reacting with a base. I'll produce water and salt and water. So I would have nitric acid. It's what? HNO3. React with magnesium hydroxide, MgHO. Now look at this. 2 there because the OH minus is not 2 minus, it's just minus. And yet I've got Mg2 plus. Mg2 plus. So this 2 here, so this 2 here, this 2 here is the one that goes down there, and this 1 here is the one that came down there. All right, so that's how we ended up with that formula there. Okay, now plus, this gives us, okay, it's going to be a salt, so magnesium nitrate. Again, the nitrate ion is 1 minus, so the 2 for magnesium will come there, plus water. Okay, can we balance this out? H2, 3, 2 there, we have a problem. Magnesium 1, oxygen 2, oxygen 5, and then plus that, okay, this is 6, plus that it's 7. So we rather than say, okay, let's balance the hydrogens first, or perhaps, then we put a 2 there. So we've got 4 hydrogens, okay, and then we put a 2 here. Then I've got 4 hydrogens. Then that 2 also means the N, I've got a 2, then 2 there. Oxygens, I've got 6, and then I've got 8, and oxygen, I've got 8 there. So this is balanced when I put those 2 2's there. There's 1 here, there's 2 here, and that 2 there leads to my equation getting balanced. Let's have a look at the next one. Sodium hydroxide and sulfuric acid. Okay, again, an acid and a base. So what do I have here? I've got NaOH, sodium hydroxide, reacting with what? Sulfuric acid, H2SO4. All right? I'm going to produce a salt and water, but what type of a salt? I need to tell from what I have here. The sodium and the sulfate will give me the salt, and therefore the salt will be sodium sulfate. Because sodium is 1 plus and sulfate is 2 minus, I will have it like that, Na2SO4 plus the water. Okay, then balance the chemical equation. Balancing the chemical equation, I've got one sodium on the left, and I've got 2 sodiums on the right, so I will need to put a 2 there so that this can be, the sodiums can be balanced out. Let me check the hydrogens. I've got 4 on the left, then I will need to put a 2 there so that I have 4 on the right as well. Sulfur, I've got 1 on the left, 1 on the right, I'm fine. Oxygens, now I've got 2 plus 4, 6. I've got 4 plus 2, 6 on the right, so it is then balanced. Okay, right. Moving on, question number 2. Lebu dissolves 1 gram of pure marble in 50 cubic centimeters of dilute hydrochloric acid after the marble has reacted completely with the marble, after the marble has reacted completely with the acid. Okay, let's just put it that way. It should be with the acid. All right. She uses 25 cubic centimeters of 0.1 mole cubic decimeter solution of caustic soda, sodium hydroxide, to neutralize the excess acid. write down a balanced equation for the reaction between marble and the acid. Okay, the marble is calcium carbonate. So the acid is what? Hydrochloric acid. So you have got here calcium carbonate plus hydrochloric acid. You are going to form calcium chloride plus water plus carbon dioxide. Okay, plus carbon dioxide. Right, now balancing it out, you had calcium 1, C1, C1, I'm fine. But then I have a problem with the hydrogen already and the Cl2 and the Cl, because I've got 2 on the right, I've got 1 on the left. So I'll put a 2 there, 2 hydrogens on the left, 2 hydrogens on the right, 2 Cls on the left, 2 Cls on the right, and 1 calcium, 1 carbon, 1 carbon, 3 oxygens on the right. So I'm fine. That has been balanced. Write down a balanced equation for the reaction between the marble and the acid. Okay, so that we have done. Okay, now, so that is that answer there, this one. Now 2.2, write down a balanced equation for the reaction between caustic soda and the acid. Now caustic soda is what? It's sodium hydroxide, it's this one. And the acid is HCl. So you've got NaOH plus HCl. You're producing the salt sodium chloride plus water. Okay, now balancing, this is balanced, so I don't have to balance it. Balanced as it is: 1 sodium, 1 sodium, 1 oxygen, 1 oxygen, 1, 2 hydrogens, 2 hydrogens. So that's fine. Now the next one says, calculate the number of moles of the caustic soda used to neutralize the acid. Now let's go back to the information that is given to us. The solution of caustic soda that was there is 0.1 mole per cubic decimeter. Okay. And then what is in excess is the acid. It means the whole of sodium hydroxide has been consumed. Okay. So if I am to calculate the number of moles, I would use the equation that says concentration is number of moles over volume. Okay. Now, this student used a volume of 25 cubic centimeters to neutralize the acid. So 25 cubic centimeters, you divide that by 1,000, which will be 0.025. Okay? Or you can just, from there, just say, this will be 25 by 10 to the power minus 3. That is your volume of the base. Okay. And then if you are to calculate for it, the concentration is 0.1 equals number of moles divided by the volume, which is 25 by 10 to the power 3. Therefore, the number of moles is equal to 25 to the power 3. 25, let me put it that side so we see that 25 by 10 to the power minus 3 times 0.1. Okay, and what do we get? 2.5 by 10 to the power 2.5 by 10 to the power minus 3 moles. That is the number of moles of the acid, of the caustic soda, sodium hydroxide, that has been used to neutralize the acid. So you can see that you need to go back to your knowledge of how to calculate for concentrations and understand how you can use that very important equation, C equals N over V, to calculate for the number of moles of the acid, of the base that was used here.
I think it's time for a break now, so don't go away. We'll be right back. Welcome back from the break. Let's not waste any more time and get straight back to today's revision lesson.
Okay, now let's have a look at the first question here. Question number 1.1, calculate the concentration. Now, if you see big brackets like that, okay, and of course this should have been like that, so the formatting actually changed it, but that is what it should be like. Calculate the concentration of the hydronium ions in each of the following. Now let's look at pure water. Pure water, okay, we know that with pure water we're talking about pH 7, something that is neutral. Okay, so pH 7, pH equals to 7, and remember there are no units for pH, and then we're saying that water is neutral. Okay, now if we are to find the concentration of water, of hydronium ions here in pure water, here basically we don't even have to calculate. We have to know this. We just have to know that the concentration of the hydronium ions, which is the same as the concentration of the hydroxide ions for pure water, would be equal to 1 by 10 to the power minus 7. But we're talking concentration, so we need to put in the appropriate unit for measuring concentration, which is mole per cubic decimeter. Okay, so that is the concentration of the hydronium ions in pure water. Coming to 1.1b, we are to find the concentration of hydronium ions in 0.2 mole per cubic decimeter of sodium hydroxide. Now, you would notice that sodium hydroxide is a what? Is it a base or is it an acid? I can hear you saying it out there that sodium hydroxide is a base. Okay, now why would I then say find the concentration of the hydronium ions in a solution that is basic? Well, the reason is, in whatever solution, when we talk of a basic solution, it doesn't mean that we don't have hydronium ions there. But what it means is that we've got hydronium ions, but in a very, very low concentration compared to their counterparts. In this case, is the hydroxide ions that are there. Okay, so in a solution of sodium hydroxide, you need to know that we do have hydronium ions. Okay, so if we're talking about finding the concentration of hydronium ions in this solution of hydroxide or sodium hydroxide base here, basically, it means that we need to understand that when we have the concentration of hydronium ions, which is a plus there, times the concentration of the hydroxide ions, this gives us a constant which is always 1 by 10 to the power minus 14. Okay? Now, if I were to find the concentration of the hydronium ions and I'm given the concentration of the hydroxide ions, it means here all I would need to do is just to substitute for that. So I'll just say, okay, concentration of the hydronium ions, which is what I'm looking for, times the concentration of the hydroxide ions, which will be the same as the concentration of sodium hydroxide. Because when you look at sodium hydroxide, when it dissociates in water, what do we get? What we get is sodium plus the OH minus ions. So if you look at the ratio here, 1 mole of that will give me 1 mole of that and 1 mole of that. So if I've got 0.2 here, it means I will have 0.2 there and I'll have 0.2 there. So it would mean that the concentration of hydroxide ions is also 0.2. So it will be multiplied by 0.2. And that should give me 1 by 10 to the power minus 14. Therefore, the concentration of hydronium ions H3O plus would be equal to 1 by 10 to the power minus 14 divided by 0,2. And what do I get? Okay, so you can use a calculator there. You don't have to crack your skull about that. So you pull your calculator and you say 1 by 10 to the power minus 14. You divide that by 0,2. Okay, and what do you get? You're getting 5 by 10 to the power minus 14. Okay, now that's a very, very small number. 5 by 10 to the power minus 14. Now this is concentration, mole per cubic decimeter. Okay, right, mole per cubic decimeter in that way. Right, and moving on, coming to 1.2. Here it says, calculate the pH of a solution with the hydronium ions of 3.6 by 10 to the power minus 5 mole per cubic decimeter. Now, pH is equal to minus log the concentration of hydronium ions. That's what pH is. So that will be equal to minus log. The concentration is what? 3.6 by 10 to the power minus 5 mole per cubic decimeter. And once again, you bring your calculator on because you just want to get that answer there. So this is equal to minus log the concentration of 3.6 by 10 to the power minus 5. Okay, you can close the brackets if you want to, and then we get what the answer is. The pH is 4,44. All right, so the pH is equal to 4,44. It's actually, you can say that this is pH of what? Of 4. Now it tells you 4 is less than 7, and therefore it tells you we are talking about an acid here. Acids have got pH levels less than 7. Bases have got pH levels greater than 7. So basically the pH is a measure of the acidity and the basicity of a solution. Okay, it tells us where do we place this substance. Do we place it as an acid? Do we place it as a base? It tells us where it is. Okay, so that is what the pH does. All right, and moving on to question number 2. Let's look at question number 2. Question number 2 says 1.6 grams of potassium hydroxide is dissolved in water and make up a volume of 250 cubic centimeters. So volume is 250 cubic centimeters. Okay, 250 cubic centimeters. All right. And the mass of potassium hydroxide that has been given to us is 1.6 grams. Now let's come to 2.1 and try to find out what they want us to do here. Calculate the concentration of the potassium hydroxide in mole per cubic decimeters. Now for us to calculate for the concentration there, we know that concentration is number of moles of a volume. What we are given is mass, so we need to find out what the number of moles are of potassium hydroxide. So I'm talking from this. Concentration is number of moles of a volume. We don't have number of moles, we have got mass. We do have the volume, and of course we will have to convert it into cubic decimeters by dividing by 1,000, and that is 0.25 cubic decimeters, because that is the unit of the volume that we work in. So this means that we need to find the number of moles here. But number of moles, again, it's given mass over molar mass. Look at what I'm doing, and I'm bringing all the equations and formulas that are going to help me sort out this problem. And once again, I see that, you know what, I still have the molar mass that I don't have, but I can work it out because I know I'm dealing with potassium hydroxide. So the molar mass of potassium hydroxide, I can find it. And how do I do that? Let's just have a look here. I will need a periodic table here. For potassium, what is the mass? There is 39. And for oxygen, we'll come to oxygen, you see it's 16 relative atomic mass there. And for hydrogen, you see it is 1. Okay, so it will be 39 plus 16 plus 1. All right, so let me go back there. So this will be 39 plus 16 plus 1. And that will give me, right? Go to your calculator, you work that out, which should be simple to do. So it's 39 plus 16 plus 1. What do you get? You're getting 56. So this is 56 grams per mole. 56 grams per mole. Now I have the molar mass. Okay? Need to make sure that you see that as per mole. All right? Per mole. Right. Now, from here I can work out the number of moles. Number of moles is given mass, which is 1.6, divided by molar mass, which is 56. And therefore, what is the number of moles here? Can then use my calculator once more to find the number of moles. That will be 1.6 divided by 56. And what do I get? Right? I'm getting 0.02857. Allow me to write it down today as 0.029. 0.029 moles. I know that we always want you to write these things to 2 decimal places. But because this number is so small, allow me to write it like that. Now I come to concentration. Okay, this concentration, it's number of moles over volume. So it will be equal to, number of moles, I've now found it, it's 0.029. You divide it by the volume in which the solution is made, it is the 0.25 cubic decimeters, so 0.25 cubic decimeters, 0.25 cubic decimeters. And what is the answer there? And once again, you're not going to crack your skull. You pull your calculator and of course get into the mindset land page there and actually work very hard so that you can get your own calculator. So this will be 0.029 divided by 0.25. And what is the answer? You get it to be 0.11. So 0.12. I'll write this as 0.12 mole per cubic decimeter. Okay? Mole per cubic decimeter. Mole per cubic decimeter. So that is the concentration of potassium hydroxide. Okay? And moving on, if 25 cubic centimeters of this solution is used to neutralize 28 cubic centimeters of dilute hydrochloric acid, calculate the concentration of the HCl solution. Now here I need to take it a bit slow for you. Firstly, I need to write down the chemical equation showing the reaction between this potassium hydroxide plus the acid HCl. Hey, the acid HCl. And what do I get? I know that every time I have a base reacting with an acid, what I am going to produce is a salt. Okay? The salt will be KCl in this case. Salt and water are the products that are formed when acids and when an acid and a base react. So this will be KCl plus water, H2O. All right. Now, when I look at this, The ratio is such that when I look at it, it is balanced as it is. So this chemical equation is balanced. 1K on the right, 1 oxygen on the left, 1 oxygen on the right, 2 hydrogens on the left, 2 hydrogens on the right, 1 Cl on the left, 1 Cl on the right. So balanced. So this tells me that for every 1 mole of that, I would need 1 mole of HCl to react with it so that I can produce 1 mole of KCl and 1 mole of H2O. So the ratio in which the acid reacts with the base is 1:1, all right? In terms of we're talking about molar ratio. This is a molar ratio, okay? Now, this, from the formula that says concentration is number of moles over volume, if I want to find the number of moles, I can say that number of moles is concentration times the volume, okay? So if I'm talking the number of moles of the acid, this will be the concentration of the acid times the volume of the acid. If I'm talking the number of moles of the base, that will be concentration of base times the volume of the base. Okay, that's what it would mean. All right, now, if I want to work out that ratio, remember a ratio, it's a division. This is the same as 1 over 1. 1:1 is 1 over 1. So basically, I can do this. I can say, let me find a proper space here. I can say that the number of moles of the acid divided by the number of moles of the base, that will give me at the equivalent point, at the point where the reaction has occurred, all right, it's 1:1. Now, number of moles of the acid is concentration of the acid times the volume of the acid. Number of moles of the base is concentration of the base times the volume of the base, and that should be 1 over 1. This therefore means that I can then substitute those values here. Remember, I calculated for the concentration of the acid, and we found it to be 0.12. But what we don't know is the concentration of the base, and therefore we can just write down what is given to us here. Volume of the base is 25 cubic centimeters. And the concentration of the base we calculated for it is 0.12 mole per cubic decimeter. Okay, and volume of the acid, we given it to be 28 cubic centimeters. But then the concentration of the acid, they want us to find that. And from here, we will be able to find that. And remember that this was not necessarily given to us directly, but we had to calculate. We only had the mass of the base, okay? And that is given to us as the volume of the base, which is potassium hydroxide in this case, and that is the volume of the acid, HCl. And we are looking for the concentration of the acid. Ca means concentration of the acid there because the subscript A talks to the acid, whilst that one talks to the base. Now, let's come to this formula here now, and let's begin to substitute into it. But before we substitute, I also want to let you know that because all I'm doing involves division and multiplication, and division on one side equals to division on the other side, I don't have to change to convert my volume values from cubic centimeters to cubic decimeters. It's not necessary because I'll still be dividing by the same numbers, okay? So I will put them as they are, all right? So Ca is the concentration of the acid. That is what I'm looking for. So I'll leave it as Ca times the volume of the acid. Like I said, I am not converting this into cubic decimeters because after all I'm dividing, so it's still going to be the same unit. All right, and then divided by what? Concentration of the base, Concentration of the base, we know it is the 0.12. We calculated for it, 0.12 times. The volume of the base is the 25 cubic centimeters. And once again, not converting it. If I decide to work in cubic decimeters, I'll have to have cubic decimeters on the top, cubic decimeters in the bottom. So I'll be having 0.28 divided by 0.25. Okay. This will be equal to 1 over 1. All right. And then working this out, this is just cross multiplication. So this will be 28 Ca would be equal to what? You come with your calculator once more, work it out there. When we say cross multiplication, that multiplies that and this multiplies that. Okay, so 1 times that remains as it is. So it's 28 Ca equals 0.12 times 25 times 1. What will that be? All right, so we work it out here. 0.12 times 25. This will be times 1, so it will remain what it is. So that is a 3. Therefore, the concentration Ca of the acid would be equal to 3 divided by 28. Then you go back to your calculator. Well, I still have the 3 there, so I'll just say divide by 28 and find my answer to be 0.11. So 0.11 mole per cubic decimeter. Okay, so I have found the concentration of the acid.
We've come to the end of today's show. Thanks for joining me and for chatting to me during the show. Please visit our website learn.mindset.co.za to get the notes and to watch the videos from earlier in the year. And remember, we are here to get you through the year, so stay connected. Goodbye.